Okay. All right. Good morning, everybody. Good to see everybody this morning. This is our second one of these technical sessions. We had a pretty good session, I think, yesterday. Just wanted to, and I've kind of typed it out so I don't forget anything, but got just a few housekeeping notes for you. My name's Laura Hart. I'm a water policy analyst with the department and also the rules coordinator for the groundwater allocation rulemaking effort. As a reminder, today's meeting is an optional technical session. We're offering it as a follow-up. And Justin, if you wouldn't mind admitting people as I'm reading through this, I appreciate it. Thanks. So this is a follow-up to our last RAC meeting we had in December. At that meeting, Ben presented some information concerning the science underlying our definition, our proposed definition for reasonably stable groundwater levels. And we also provided a written memo that summarized that information Ben presented. And that memo's also been given to the U.S. Geological Survey to get their input, which I think we're expecting that input any time now. And Justin may be able to speak more to that in a moment. Today's meeting is going to focus just on reviewing that material, that technical information. RAC members were asked to submit questions ahead of time if they could, and Ben did his best to take a look at those questions and incorporate those questions into his presentation in order to address those questions or comments. We're going to ask, although we're pretty informal here, we're going to ask RAC members to wait until Ben gets through a given slide before raising a hand and asking a question, just so he can have the space to, get through his explanation. We're going to ask the public to hold their questions until public comment period, which we'll pause around 10:15, depending on how, the flow of the meeting, and ask if any members of the public would like to ask questions or provide a comment. Again, want to emphasize, please limit questions and comments to the scope of what we're talking about today. That is that technical information. If you wish to submit comments or have questions about other aspects of the rulemaking, you can submit those to me in writing. I'll drop my email in the chat as we get started here. You are also welcome to join us. We have our next RAC meeting scheduled for January 23rd from 8:30 to noon. It's a hybrid meeting. It's open to the public. We have a designated public comment period, so you're welcome to join us there. The meeting materials will be available prior to the meeting, and I'll post the link to our rulemaking website so you can see where you can find all that information if you need it. Just a reminder, the meeting's being recorded, and we'll be posting the meeting today is being recorded, and we'll be posting it online. The meeting from yesterday is already up online and available for viewing. So I'm going to turn it over to Justin to see if he's got anything to add, and then we'll go ahead and get started.
Yeah, thanks, Laura. Nothing to add. I just want to reiterate two things again, repeating what Laura said. We're holding these meetings as a follow-up to requests from RAC members during our RAC number 7 to discuss more in depth the technical process Ben went through to quantitatively assess past hydrographs to inform our rule definition of reasonably stable water levels. The RAC 7 presentation was more general, whereas this is going to be more technical. So we haven't attempted to make this universally available. So just want to give folks a heads up on that. And looking forward to, again, meeting the request of the RAC members to have more time for Q&A with Ben and Laura and I. And if folks that are not on the RAC have comments, we ask that you hold those comments till the public comment period, roughly 10:15. We'll check in with everybody to get those. And with that, I'll pass it over to Ben to get started.
Thanks, Justin and Laura, and welcome everyone. And I want to start by saying, as I share my screen. Thank you to all the RAC members who have been engaged in this process, given feedback at the RAC meetings, and submitted questions and comments last week ahead of this so that I could prepare a few slides to guide the discussion and answer some of the questions that are best supported by some additional figures. I haven't answered every question that was submitted. There were over 30 questions and comments. I haven't given a specific answer to everyone in the following slides, so I look forward to the Q&A session after I present these slides, that it'll be more freeform. But I hope that I've at least addressed many of the major issues that were brought up. So with that, let's get started. And just checking everyone can see the presentation slides that I'm looking at. Great. Here's a quick review of the schedule we're looking at for the next hour and a half or so. I'll be giving the slides in the methodology. We'll transition to Q&A. Of course, after each slide, I'll try to pay attention for folks who have raised their hands, RAC members who have raised their hands in Zoom here, and Justin and Laura can interrupt me if I miss that. And then we'll do public comments and wrap up at 10:30. So many of the slides I'll show today, including this one, are ones that were shown also at the December RAC meeting. So I'll go through those a little bit quicker with less discussion, but I thought that they were worth bringing back up to provide context for the larger discussion we have. So this slide lists a few of the major objectives that the department started with when developing this definition of reasonably stable groundwater levels, including that it should be consistent with the interpretation that a trained hydrogeologist might make looking at a hydrograph. It should be consistent, that is, avoid switching between finding reasonably stable and not when water levels are within the dynamically stable range, which is something I'll talk about in a moment. On the other hand, it should also be sensitive to clear water level declines. It should rapidly transition from indicating water levels are reasonably stable to no longer reasonably stable. The definition should limit and explicitly define the burden of collecting additional water levels. And finally, it should be transparent and easy to implement. And I really want to appreciate some comments by RAC members highlighting the difficulty of balancing the tension between some of these objectives, in particular between consistency, remaining reasonably stable in cases where we think water levels should generally be reasonably stable, and also sensitive to declining water levels. The work that I'll be presenting today mostly addresses that consistency objective. We're going to be looking at some water levels that are from one perspective, a priori said to be reasonably stable, and see how well the proposed definition remains consistent in its ability to classify those as reasonably stable. But this slide puts that work in the context that there are many other objectives for this proposed definition to meet, and this is but a small part of how to determine that, and it's not the only way to look at the problem. The dynamically stable range is a term taken from modern scientific literature, thinking about water level fluctuations in the context of natural resources management, that water levels do fluctuate for a variety of reasons, including both natural and anthropogenic causes, and that sustainable resources management can require that water levels remain within this range that's illustrated in this graph here, this time series from today through multiple generations on the x-axis, and on the y-axis are water level elevations. The dark blue line is a a hydrograph, a water level time series for groundwater levels, and the light blue bar behind it is this dynamically stable range in terms of the absolute elevation of water levels. So a big piece of the work I'm presenting today is understanding or estimating how tall that dynamically stable range, how tall that blue bar should be in order to capture the observed variability in water levels, such as we're seeing with the dark blue lines. We'll look at a large set of wells that we believe satisfy this long-term stability requirement. And the other red and yellow lines here show other management approaches that aren't consistent with this maintenance of water levels within a dynamically stable range. Perhaps the most frequent, most common comment or question that came up was specifically on this question of natural water levels versus stable water levels. And this is understandable because the department previously has described this work, this attempt to characterize the variability we see in water levels as looking for natural variability. And in the process of doing this work, we've realized that that's not really the most important question to try to distinguish between which variability is natural and which variability is anthropogenic. There are hardly any wells in Oregon at this point that aren't influenced to some extent by human activity. Even wells that have a strong influence of something like precipitation cycles, which we'll look at for most of this presentation, many of those are also influenced by human activities, such as during a year or period of years when precipitation is relatively low, that tends to increase groundwater pumping because there's less surface water available and maybe drier soil moisture. So more demand for groundwater, and that additional pumping can cause groundwater levels to decline further than they would have already due to the reduced recharge from reduced precipitation. So inferring the causes of declines is generally a difficult problem and not one that we can expect this proposed definition of reasonably stable groundwaters to accomplish. Instead, the approach looking at of wells and their behavior, just saw a note that my connection is unstable. Did you all lose any content I just stated?
No, I
Just a
think
little
we
bit?
picked
Okay,
it up, but we heard, yeah, it did cut out for a sec.
thanks. I'll back up just a bit. So inferring the causes of groundwater declines is a difficult problem that we can't generally expect the proposed definition of reasonably stable to accomplish because we're trying to keep it simple. Even expert hydrogeologists with sophisticated numerical simulation models can have a difficult time inferring what are all the various causes of groundwater level declines. And instead, the department's approach with this proposed definition is to set thresholds so that are appropriate to distinguish between water levels that could be reasonably expected to recover based on observed behavior in wells around the state. So for that purpose, it's not so important for us to find natural variability or wells that aren't influenced by humans at all, but instead to look for wells that have some fluctuations and also recover back so that they are varying around a mean level that is stable through time. So I'll pause there just to check in case there are questions so far. All right. Reviewing a slide from Rack 7, here are the major elements of the analysis that is in the memo and we'll be talking about today. We look for water level trends, water level records in wells that represent stable conditions. That is, they have fluctuations that are correlated with precipitation averaged between 2 and 10 years, looking back, a moving window average. And that's how we look for that in order to capture fluctuations that we know we want to include as potentially reasonably stable, while at the same time requiring that the long-term trend over the entire period of record has to include both at least 25 annual high measurements, and that the trend over those at least 25 measurements needs to be less than half a foot per year of decline. Once we've identified wells that meet those criteria, we do some work to process the data and help them be a representative sample of the stability that we're trying to characterize. To do that, we actually remove that long-term trend so that declines or even water level rises are shifted so that they actually do vary around a center that remains constant through time. And we also cluster wells whose behavior is similar and whose location is similar, as well as to the extent that we know could be in the same aquifer, in order to reduce bias from overrepresentation of the same water level signal measured from multiple nearby wells. So you'll hear me talk a lot about clusters in the following presentation. And when I talk about a cluster, I mean any number of wells that could be one well, could be two wells, could be I forget what the largest cluster is, could be up to 20 wells who are nearby and behaving similarly from the perspective of this analysis, so that we don't want to double count them, and instead that cluster is treated as if it's just one well. So once we've removed those best fit trends, and that also I've been calling that detrending, once we've done that and clustered the wells, we evaluate for each of the wells what is the total decline. And by total decline, I want to distinguish here between that and the long-term best fit linear trend. There was a great question yesterday that identified how my language around this is sometimes confusing or so similar that it's easy to conflate the long-term trend over the period of record, which is something that's removed from the data set, versus the total decline measured from any year looking back to any previous year, which is one of the tests built into the proposed definition of reasonably stable. So I'll try to use the term total decline to refer to one of the metrics that's being evaluated in the following analysis as different from the long-term trend that gets removed from each well. In addition, for each year in the period of record, we evaluate a rate of decline according to the form of the proposed definition of reasonably stable, and we'll talk more about that later, with the intent of being able to characterize what those measurements of total decline and rate of decline would be from the perspective of the proposed definition, so that we can set thresholds on those maximum allowed values consistent with reasonably stable that will encompass the vast majority of this water level behavior that is stable in the long run. To statistically characterize that, we'll look at both the maximum values in each well for the total decline and the rate of decline among all the years in the period of record as a way to characterize the value that best represents that well. And we'll also look at the percent of the time that those total declines and rate of decline are less than particular values among their period of record.
So Ben, before you go on, there's a question from Kate. Kate, I don't know if you want to just unmute yourself and go ahead and ask your question.
Just a simple question. When we're talking about water levels, are we talking about the same season for year to year, or is it water levels throughout the year, throughout the period of time?
Thank you. Yeah, all of this analysis is focused on annual high water levels, which is something we've discussed with the RAC. And those are, for the purposes of this analysis, measured between January and April inclusive. So it's for each well, the annual high water level is the shallowest water level that was measured during any of those 4 months. And it also excludes water levels that were determined in the field to be influenced by pumping, because maybe you observe nearby pumping, you see that the water level is still recovering, or in some cases when staff have been able to, through a separate process, go and review water level records, they're able to classify them in terms of their plausibility and reliability based on their understanding of the hydrogeologic system, so that the annual high water levels are the department's best assessment of the highest water level that existed in a given well in a year.
Thank you.
So before we go on, I just wanted to acknowledge Kate is sitting in for Kelly Warren. So she's a proxy for a RAC member. So Kate, I wanted to clarify that. So if you have questions, please raise your hand as we go through.
Thank you and welcome, Kate. All right, carrying on then. So I'd like to just show a few examples of the detrending process, since there were a couple of questions from RAC members about how that works. Each of these 4 figures on this slide represents one well, and each is a time series of water levels from 2 different perspectives. The right axis and the purple color is the raw water level elevation data, again, annual high water levels in each case. And the dashed purple line is the least squares best fit linear trend through the entire period of record. And the black line and the left y-axis is what you get after subtracting that best fit trend from the raw data to get what I'm calling the detrended water level record. So the detrended water levels are what are analyzed for the purposes of the following work. And the removal of that trend helps us bring these water levels to as close a representation of what we think stable water level behavior should be, that we also know we generally want to capture, to allow the proposed definition to remain generally consistent in its findings that water levels are reasonably stable if water levels are behaving like this set of wells that were found. So here are a few examples with relatively minor long-term rates of change shown in the titles, negative 0.1 foot per year or 0.1 feet per year. If we look at a few more examples, we can see some faster rates of decline, ranging from 0.2 to 0.5 feet per year. And the resultant detrended water levels. In my mind, the most striking example is in the top right with Lake 4437. And you see that this detrending has a relatively large impact because the magnitude of the fluctuations around that long-term trend are relatively subtle, so that the the behavior looks significantly different after detrending. But really all that we're doing is making sure that we're evaluating behavior that exists on top of that long-term trend. And for the purposes of this analysis, we set, based on professional judgment, looking at a lot of hydrographs, 0.5 feet per year as the maximum allowable rate of decline that is consistent with reasonably stable, because over potentially 25 or more years, half a foot per year becomes 12 feet of decline. That's reasonably significant from the perspective of other impacts that we're looking at. And it's hard to argue that even a detrended water level record that started with a rate of decline of half a foot per year, of more than half a foot per year, is really representing stable behavior statewide. So this was, yeah, please, Kate.
I'm sorry to interrupt, and I'm sorry for this very basic question, but once you detrend the water levels, is it now the point to have a stable set of conditions in which to evaluate future water level declines, or if they occur? So you're looking at a base set of conditions and then using that for future assessment?
That's exactly right. In this analysis, the past is the key to the future. We're designing the proposed definition of reasonably stable, looking at historic behavior and assuming that that will be a fair way to characterize the robustness, the expectation that water levels could plausibly recover if they were remaining within the behavior as characterized similar to this existing set of wells.
Okay, so this is determining and defining your range of variability of stable conditions. Is that correct then?
Very well put.
Okay, thank you.
So we did this detrending for 234 wells that met the criteria in terms of limited long-term declines over their period of record and sufficient correlation with precipitation, regional precipitation. And I'll just show a few examples that we looked at from the RAC 7 meeting. Here's one of the wells that we started looking at from the very beginning of this process, Deschutes 3016. The right y-axis and the blue dashed line is the long-term, or the regional precipitation record, in this case averaged with 6 years moving window average. Any well was considered sufficiently correlated if it had an R² of at least 0.2 with any regional precipitation record, or the regional precipitation record averaged over any backward looking moving average window of size 2 through 10 years, based on evaluation of hydrographs statewide. That seemed like a generous way to capture the vast majority of observed behavior, and that flexibility allows for variable behavior between aquifers around the state, so that the time between water falling on the ground, precipitation, and flowing towards the wells, recharging the aquifers in the areas where they're being measured by these wells, is allowed to vary between 2 and 10 years without constraint for this analysis. And the figures that I'm showing here, the titles display the best correlation. The values in the second row of the title show the resultant values, statistical or values over the entire period of record for the total decline, also stated here as characteristic magnitude, as well as the rate of decline. In this case, the largest total decline from any measurement to any subsequent one is 20.8 feet, and the largest rate among the eligible years is 0.3 feet per year.
Okay, so we have a question from Bill before you move on.
Thanks. Ben, I just have a couple of clarifications. You mentioned regional precipitation. What's the spatial resolution on that? Does it vary? I mean, you have some wells from all over the state. Is this, yeah, I guess how narrow is a spatial, I guess, average precip is this using?
It's fairly coarse. I'm using the NOAA climate divisions. There are 7 or so statewide. Let's see if I can pull it up here. So here are the, 9 region climate divisions in Oregon.
Okay.
So there's like Central Cascades, Willamette Valley, Central, Southwest Coast, that sort of size. And a number of observation points contribute to each of those climate divisions.
Okay. My other question was on terms of the temporal average. I guess you said this, but I'm just wanting to make sure so you're averaging previous precipitation over 2 years or 3 years or 4 years up to, I guess, 8 years. But you're not like running a regression where you put in last year's precipitation and also separately to the precip from 2 years ago and from 3. You're not having a set of lags as part of any analysis of what that R squared might look like.
Right. It's not like I'm trying to build some sort of regressive model based on different lags. The assumption is that for a given well, the time scale for flow between the recharge zone and the part of the aquifer being observed is going to be fixed for that well, because it depends on things that don't change with time. So that it might be slow. There right. Certainly could be averaging processes that cause it to be delayed and smoothed in time. Is that addressing your question?
Yes, and it raises a related one. So you might find that the best fit for one well is a 2-year average, and the best fit for another year for a different well is a 6-year average. It sounds like you're saying.
Exactly.
Okay. All right. Thanks.
Yeah, we started trying to impose just one averaging period statewide and recognized that missed important local variability. So that was a major change between RAC 6 and RAC 7 as part of this analysis, and it allowed us to substantially expand the sample size of wells that met these criteria. Thank you. So just a couple more examples of this correlation between the detrended water levels and the precipitation record. Yamhill 4640, you'll know this, the y-axis on these is quite different. So as the previous example, the total magnitude of drop was just over 20 feet. Here it's nearly 50 feet. And best correlates with a different time scale for averaging of precipitation. Another example shows an effect that is included in the data set, which are some relatively extreme events like the declines between 1990 through 1994 or so in Sherman 340. I wouldn't say that, or the correlation with precipitation seems meaningful even without the significance of that particular drop here. In this analysis, we didn't exclude these large drops just because they happened to be exceptional. We thought about doing some outlier rejection, but decided that to do that over the entire data set would add some subjectivity that we didn't want to. We did at least take a look at all the wells with large total magnitude of declines, just to check that these water levels weren't obviously flukes. There are multiple water levels in addition to these annual highs. There are also, I don't remember if in this well, but in general, there are other water level measurements from other seasons that substantiate these as not just errors in measurement or one-off happen to be influenced by nearby pumping immediately before. So there are some of these records where the statistics, the largest values on the period of record, are influenced by extreme events, maybe not fully representative of the typical behavior in a well. But I also don't think that but there are also I would say most of the wells included in this sample look qualitatively more like this. They're not just dominated. The behavior is not driven only by a single event. So that's
Can you pause just for a second? Sorry, Kate,
course, yeah.
do you want to go ahead and ask your question?
Okay, sorry for the interruptions again.
no problem. That's great.
Are the water levels measured with transducers or by hand? And it's easy to sort out the recently pumped wells if it's a transducer and takes multiple measurements by hand.
Most of these wells were not measured by transducers. I could guess that it's maybe 10% of this set had a transducer in them. We have somewhere between around 250 wells with transducers run by the department these days. But many of the wells that are monitored by the department are also ones that are heavily influenced by pumping. They're in areas where the department is managing groundwater resources, and water levels are not generally, or at least not typically, stable in the long run in those areas. So I would say that and for the purposes of this analysis, we didn't require that water levels only be measured by the department. Some of these wells have water levels. Actually, I should check that. I'm not totally sure, but in principle, we could have data in here that were submitted by permit holders as a condition for their water right. I think the requirement for the record including at least 25 annual high measurements means that most of these are going to be wells that the department or the USGS has been prioritizing monitoring for and putting staff resources into, just because we haven't had the requirement for submission of water levels as a condition for permits around long enough that we have a substantial number of 25-year records from permit holders.
Right. The question about, or the statement about outliers is what prompted that question. I imagine the outliers are coming from hand measurements and less so from transducers. So just a assumption. So, okay, thank you.
And I think that was our first assumption too. First blush response of having looked at the data like in this well that were candidate outliers was that they are not measurement errors. Just some interesting effect of local or enhanced pumping during that period or something like that.
Okay, thank you.
Now let's look at the clustering of wells for the purposes of this analysis, in many cases, a water level trend is measured by more than one well. Such as in Josephine County here, these 3 wells were clustered based on their proximity. You can see they're each within about a mile of the central well. And the fact that their characteristic, their total decline from any measurement to any following one, was within 30% of the mean between any pair. So these 3 were found to be similar both in location, behavior for the purposes of this analysis, and because the department had, through a separate process, identified the primary aquifer accessed by each of these wells, and they're all accessing the Grants Pass Pluton aquifer. So the combination of those 3 allowed them to be clustered, and their behavior as a cluster was characterized as the mean among their the values from each of the component wells. So these wells had total declines of 8.1 feet, 10.1 feet, and 12.8 feet, and the composite behavior of the cluster was treated as if it was one well with the mean decline of 10.3 feet. So that helped to reduce the spatial bias that existed without this clustering. Not so much, not quite as problematically in Josephine County, mostly in Klamath and in the Willamette Basin. But this clustering was able to substantially reduce that. There was a question from a RAC member about whether the clustering method had the potential to over cluster, as in to include in a cluster a well that shouldn't properly be there because it might be in a different aquifer. And the answer is yes, that's possible. If a well doesn't have an aquifer picked yet, which is the case for the majority of the wells in the groundwater database, then it is a candidate to be included in a cluster with other nearby wells that also have similar values for the purposes of this analysis. So that's a review of the methods. Let's look at some of the results. First, the total decline test. As I mentioned previously, this is different from looking at the long-term trend over the period of record. Now we're looking at what would be evaluated according to the proposed definition. In each year being evaluated, it compares the annual high water level against in the proposed definition, at least as proposed in RAC 7, we would be comparing it against the pre-development water level. In that case, or in the majority of cases, the department would likely determine that pre-development water level using the previous highest known value, because in most cases, water levels have declined from pre-development values. We're still working on a definition, or we're for pre-development, and stay tuned for RAC 8 about how all of this will shake out. But for the purposes of this analysis, because for the purpose of this analysis, water levels were compared against the previous highest measurement for the sake of estimating the total decline in a given year. And I think that that's, well, the reason why that was chosen is because if we're looking to define the dynamically stable range, the range should be measured from the top of the stable behavior to the bottom. And many wells begin their measurement record somewhere in the middle. So if one was to say, we're just going to use the first measurement in a well, that would not necessarily give us a good estimate of the range of water level behaviors in that well. If you do that analysis for each year, look for how much water levels have declined from any previous water level measurement to that year, you can define a decline for a given year in a given well. And if you then aggregate those values over the over the entire record for that well, by taking the maximum among them, you get this plot here, where the x-axis is the total water level decline, and the y-axis is the percent of those well clusters, which could include one well, whose maximum value is less than that. So for small values of water level decline near the left side, there are very few wells whose maximum decline is less than that. But as you loosen the threshold by moving right on this, you include more wells whose maximum total decline among their period of record is within that threshold. And the 90th percentile, the value at which 90% of the wells have a maximum value less than that, is about 24 feet. We also looked at how these characteristic values for each well varied statewide. On this map, the color scale indicates the maximum decline for each well, where yellow, orange, and red are values over 25 feet, and green and blue are values under 25 feet. And you can see that there are a range of densities of wells in the different basins around the state, and also the wells that exceed 25 feet are scattered all around the state. So there are potentially interesting questions to be investigated about the variability between basins, but the limited number of wells in many basins makes it hard to make general statements. The fact that we see a wide range of maximum declines in each of these basins is part of the reason why the department is continuing to propose statewide thresholds for these values. Yeah, Bill.
Yeah, I'm trying to make sure I'm following the metric here. So total decline is from the highest, in the past, there's a highest measure, and you're comparing that to the lowest, more recent measure.
Yeah.
And that's gonna, so I guess I'm trying to think how to interpret that, because you may have clusters or wells here where that span of time is 10 years or 20 years or 40 years. And so total decline over 40 years might be interpreted somewhat differently than for 15 years. But I guess it's still meaningful. It's just one has to think about how that difference in length of time might influence the measure you get for a particular well, I guess. I'm not saying it's a problem. I just hadn't thought that through. Okay, that clarifies.
Thank you. That's an interesting question. I think the hope was that by removing the long-term trend from each of these wells, we would limit the influence of the duration on these statistics. But it's a worthwhile question about whether there is, in fact, still a remaining influence of the duration.
Yeah, I see your point. I had sort of forgotten about.
So there's another perspective that you can use to look at these total declines, which is, rather than asking what's the characteristic total decline for each well, looking at the maximum value, ask, what's the percent of time that wells would remain within a given threshold, averaged over all the well clusters? So if you look at all of the clusters, you get this blue line, and see that the for small values of that total decline, it's a small percentage of the time that the wells remain within that limited narrow threshold. But as you widen the threshold, as you increase the allowable total decline, you have wells spending a larger percentage of their period of record within that threshold. So that while 25 feet is roughly equivalent to a little more than 90% of the wells being always within 25 feet, that limit corresponds to wells on average being 99% within that limit over their period of record. And even if you were to look at the wells that fail the total decline test at a given threshold, so if among the wells that at some point exceed 25 feet of decline, something like 86% of the time, those still remain within the 25-foot envelope. There's more that I could say about that, but I want to keep going. I'll note that we looked at the sensitivity of the results to a number of things that you can read in the memo, including correlation with precipitation, which sort of speaks to the question of how important it is that we are capturing fluctuations correlated to some degree with precipitation, and the distributions are relatively stable in the lower percentiles. The 90th percentile fluctuates between about 20 and 30 feet, between a range of R-squareds from 0 to 0.5. The lack of a monotonic trend in that dependence suggests to me that there may be effects driven by the particular wells that are included in the set, especially as you increase the minimum R-squared towards 0.3, 0.4. You can see on the y-axis of the lower figure that the number of wells that qualify for this analysis, or excuse me, number of clusters. So this is not just number of wells, but after they get subsequently clustered based on proximity and behavior, the number of clusters drops significantly. And I think that that small sample size is a large part of why you see this variability at higher minimum R-squared values. So let's look at the rate test. There were some questions about how the rate test works. So to illustrate that, let's look at the hydrograph of CLAC 6388, which is colored in the shaded background according to the reasonably stable determination as of RAC 6. So the gray on the left is insufficient data. You don't yet have a time span of 5 years for evaluating the rate test. The following few years, it's not reasonably stable because it fails the rate test. And then after that, except for the 1 year with insufficient data because the gap becomes too long, it remains reasonably stable. So let's look at a couple of years for how that rate test works to understand why the test works like it does. Looking at 1968 on the left side, broadly speaking, we're able to compare over 2 time windows. The time windows can be anything from 5 years, up to 5 years in the past, to up to 20 years in the past. So the first lowest orange line here is comparing water level data spanning 5 years. And over that period, if you were to make the trend only using the endpoints, which is not necessarily the best method, but it's good for illustrating, the rate is steeper than half a foot per year. And it's also steeper than a half a foot per year if you include the previous data point, averaging over a 6-year period. So because both of those are steeper than half a foot per year, the shallowest among them, the slowest decline among them, is still greater than half a foot per year, and the water level fails the rate test in that year. For contrast, we can look at 2005, when the first vertical line on the right is that year, the second one going back is 5 years in the past, and the third one to the left is 20 years in the past. So if you average over data over only a 5-year period, it's steeper than half a foot per year. And that continues to be true as you go back a few more years. But if you include the water levels averaged up to a period of up to 20 years in the past, there are a number of them that have an average rate shallower than half a foot per year of decline. And the least steep of those is slower than half a foot per year. So this water level passes the rate test. And that's why the water level record remains stable over this entire preceding period, both because there are water levels that are relatively low. You're sampling over multiple cycles, or a full cycle of this precipitation-driven behavior, or precipitation-correlated behavior, excuse me. And because you're able to average the declines that you do see over a longer time period. For the purposes of this analysis, one moment, Kate, I see you. We will be looking at quantifying this shallowest rate, the flattest slope between 2005 and it looks like 1988 or so. That rate of 0.2 feet per year of decline is the one that will define the rate test value at this year of 2005. So, Kate?
Thank you. I didn't mean to be so dramatic in the video. So when I look at this hydrograph, I am imagining how it might be portrayed with an earlier graph when you were looking at the dynamic stable range calculations. And if you took the water level data for the first 30 years, 40 years perhaps of this record, and determined a dynamic stable range, and then applied the latter data to look at the rate of change, I just wonder what you would see. You know what I mean? A what if kind of assessment. Does this methodology work? You know what I'm saying?
Let me see if I get it. I'll try to restate what I think I heard and tell me if I got it right. It sounds like you're suggesting we use the earlier portion of this hydrograph, or in principle any hydrograph, and then use that to understand the later behavior in that well?
Yeah, you could take the first 40 years of this record, determine a dynamic stable range, and then compare it to the last 20 years and see if it falls within that dynamic rate. I'm having a hard time determining whether or not this is a water level. These are water levels that are stable. But, you know, visual impact, yes, it looks stable. And are these uncorrected water levels, by the way?
In this particular hydrograph, these are uncorrected. Yeah.
Yeah,
These
so
are
it,
not trended.
yeah, I'd like to see this as an application
I guess,
of the rate test.
may I jump in just to
Please.
ask, can you just go back one? You have just the hydrograph shown one slide back, right? So I guess, Kate, getting to your question of like testing it, like this is application of the proposed definition of reasonably stable water levels to an example hydrograph, to an example real world data. So essentially that's what we're doing, is we're testing the proposed rule against a known or a historical record to just see how it performs and whether that intuitively makes sense, right? So we've got water levels going up and down here for what? Let's just say 10-foot range, right? So for this particular well, we've got a roughly 10-foot dynamically stable range. Now we've said we're going to allow, like, we want a statewide rule. We want a rule that covers a majority of wells across the state, and it's actually 25, right? Plus there's a rate, and what Ben is showing is the rate portion, not the total dynamic stable range, right? Or the magnitude portion. And so what this is showing is, looking at 1960 roughly, we don't have enough data, right? Our rule set says you have to have 5 years of data. And then once we do have 5 years of data, it actually shows, well, hey, based on overall what we've set up as the rule set in that orange bar in the late 60s, it actually doesn't pass the test. So if we were looking at this rule set and we put our hand up and covered up everything back to 1970, we would say not reasonably stable. And as the record builds and we get more data and a longer record, then that flips, and the blue shading shows reasonably stable, and that gray bar in 2013 shows, oh, we had a gap in the data and we don't have enough data to make this analysis anymore, enough modern data, right? So you need one more data point and then it's blue again, right? So this is an assessment year by year by year, and you could back this up any number of years and just say, and this is the problem we're trying to solve for, is we're looking backwards to test the rule set for how it's going to perform looking forward when we have much perhaps less data, right? Like when we might be on a falling limb or a rising limb, how is it going to look? And this is an example of how it's going to look. So does that address what you're getting at? Sorry, you're still muted there.
I appreciate the explanation, because of that orange bar wasn't clear to me.
Okay.
But now just looking at this particular example, we have what appears to be a stable water level range, just flat out. And you're right about the first 5 or 10 years, you wouldn't be able to determine this stability because there's insufficient data. But the first 30 years, 40 years, take that data and do a trend correction, which there probably won't be much of a correction, but do that trend correction, determine that range, and then look at the last 20 years and see that, yes, indeed, it does fall within the dynamic stable range. And this is a good test for that, given the length of record. There are wells in the Umatilla River Basin that have this length of record, and they have water level declines to go along with it. So if you took the first 40 years of a Umatilla Basin well, did a correction, and then applied the last 20 years, you may see it falling outside its dynamic stable range. Or you may find it does indeed fall within the dynamic stable range, because some wells are stabilizing. So anyway, I'd like to see the dynamic stable range calculations applied to wells with a long period of record. Like this. Does that make sense?
As far as
Let's
yes,
keep going.
I think what you're saying, what you're saying makes sense. Thank you very much.
Okay, we could keep going. I'm sorry to interrupt. I was jumping ahead, wanting to see the application to long periods of record and seeing how well it fits our intuitive sense of it all.
And Bill, go ahead.
Yeah, so this graph is maybe a good illustration that leads me to one question I've had. You're pointing out that if you only have the first few years of data, according to your rate test, before 1970, you'd apply the test and you determine that this well is not stable, this water level is not stable because the short time frame of data. But so one of the things that keeps coming up in the back of my mind is, well, but if you have other data, if you have data on other wells, for example, wells that are nearby, and can think about sort of pooling data, you might, and with a rule that took into account how did the nearby wells look that are maybe, maybe there were 3 drought years in a row here, and so a more pooling of cross section. You've got a time, so you're trying to look at you're doing a time series analysis, but there's a cross-sectional dimension that could strengthen the power of your statistical tests. And this is one where, gee, if you had some wells maybe in the same climate zone, but a different aquifer, the explanatory power of saying, oh, well, yeah, this fails this test, but if we had a way of thinking about how other wells in that region also look pretty bad this year due to precipitation in those years, that would help us understand better why this maybe isn't evidence that this water level is just headed farther down.
Thank you, Bill. It definitely makes sense. And I really have appreciated throughout this process your emphasizing the importance of considering water level data from surrounding wells. I did a bit of reading about panel methods when you first suggested that earlier. And while we didn't try to define in rule how that process should be done, because I think that would make it quite complex. Like you need some detailed work to decide how that should be applied in each case. We did write into this proposed rule the flexibility to do precisely what you're suggesting. And the way we did that is to define reasonably stable, not with respect to a well, but with respect to an aquifer or groundwater reservoir or part thereof. And from our perspective, what that means is that as we're evaluating reasonable stability, we can evaluate it well by well, as in this example we're looking at, or we can build composite hydrographs based on multiple wells. I don't have an example right in front of me. I might be able to pop it up while we're doing a discussion later, but can build composites in order to evaluate this test using not just data from a single well, but when we have data where we can correct them into we can reconcile them, I'll say, in order to evaluate reasonable stability over the composite record, there's room to do that.
Thank you. That makes sense.
Yeah, I just want to note there's a suggestion from Kate. I don't know if you want to state your suggestion, Kate, or
oh no, let's just
chat?
keep going. This is
Okay.
a good technical discussion. Thank you.
Okay.
Also, I'm just noting the time and the interest in getting some room for public comment too. I am happy to continue on past 10:30 with more of the detailed discussion, but I also am curious if we want to postpone public comment until after finishing these slides, or take that now and then I'll finish the slides after that.
Can we just gauge the folks that are joining us that are members of the public. Does anybody foresee having questions? And again, we're going to limit the discussion to the materials presented today. I'd like to complete this discussion. Okay, that's Kate. Yep. I think maybe keep going because I think it probably makes sense for if folks, want to hear all the information and then have an opportunity to ask questions.
Fine with that. All right. So what you get if you run the rate test, sorry, the coloring here between orange and blue for these slopes is useful for running the rate test in the full sense that it's run in the proposed definition, i.e. you get a slowest rate of decline for each year, and then you compare it against a reference level. In this example, we're assuming that the reference level, or the threshold maximum rate of decline is 0.5 feet per year. That's still pending review from the USGS and considering RAC input. But for the purposes of the analysis that I'm going to show in the following slides, we don't take that final step of comparing it against a particular maximum value in order to say yes, no, but we just quantify what is the shallowest rate of decline for each year, looking at averaging periods between 5 and 20 years preceding. And so we get a time series of annual rates of decline as measured with this rate test. And that's what I'm going to show in the next slide in purple. On the right axis is that annual rate of decline according to the rate test. So in each case, it's the minimum among those averaging periods looking back 5 to 20 years. And the time series is increasing downward from the top. And you can see that during those first few years, the rate of decline is relatively fast, in large part because this well happened to begin its measurement during a falling limit of this decadal cycle. And then following that, for the remaining years, the rate of decline is either zero because there's no decline comparing with those previous data, or it's much lower to the tune of 0.2 feet per year during the bottoms of these troughs. And a piece of this analysis that's discussed in the memo but didn't have time for in the RAC meeting is the limitation on the following analysis, which says that we need 10 years of data in order for this test to operate as intended. So the rate test as proposed in rule is allowed to be run following only 5 years of data, or data spanning 5 years. And that's a choice that the department is making in order to meet the objective of limiting the burden of additional data collection in areas where we don't already have data. But the test is intended to be able to average over these precipitation cycles, which in Oregon are dominantly decadal. So really, it's intended to be run when you have 10 years of data. And what that means is that the characteristic rate for this well would be not 1.3 feet per year if you were allowed to start at 5 years, but it's 0.2 feet per year starting at 10 years. And another example of that here, this is again Deschutes 3016, which we've seen a few times, also begins its measurement without having completed a cycle. So you're not able to look back at a previous low water level, and those early measurements are relatively steep according to the rate test compared with the following ones. So
sorry, Ben,
Yeah,
did
Bill.
you say that the purple line, that's an average of decline over the previous X years? Is that what that is?
The values in the purple line are the ones that you would get applying the rate test. So it's the the shallowest rate of decline among the data averaged between 5 and 20 years previous.
Okay.
So for the year 2005, that shallowest rate is 0.2 feet per year among, or roughly, among the potential matches with the rate test. Does that make sense?
Yeah, I think so. But on the next slide, I was trying to make sure I understood what the purple line is. And that's not just an individual year's annual rate of decline. It's an average of, maybe I'm misunderstanding.
Yeah. So the rate test does averaging. The rate test finds average rates of decline over some period.
Okay.
It tests a bunch of different averages, anything from 5 years, 6 years, 7 years, up to 20-year periods, using the available data leading up to the year being evaluated. And the value in this pink line is the shallowest decline among those for that year being evaluated.
Oh, got it. Shallowest. Okay, that's what I. Thank you.
And that's the metric that's being used for the following analysis to characterize what the maximum allowed rate of decline should be in these statewide rules in order to maintain these wells, which we've said a priori represent reasonably stable over their periods of record. So there's some analysis of the dependence of the results on that minimum span. Read the memo for more. This is the figure we presented in Rack 7, showing that those characteristic rates per cluster, that is the maximum rate of decline among the eligible period, they increase. The more wells fit within that limit as you increase the limit to the right, and 90% of the wells are within, I think it's 0.64 feet per year over their entire eligible periods of record. The orange line here compares the proposed rate test against a standard statistical test, the Mann-Kendall test, which with alpha is 0.05, it characterizes fewer of the wells as stable over their entire period of record. So applying the same type of metric to the Mann-Kendall test as we are with the rate test, what we see is that the department's proposed rate test in the range of 0.5 to 0.7 feet per year that's being considered for the maximum allowed rates. The proposed rate test is less sensitive to declines. It is more consistent in its ability to characterize these wells as remaining reasonably stable over their period of record than a standard statistical test. And I think that reflects the structure of this entire exercise, which is, as some RAC members have pointed out, tailored to characterize and limit what can be called a type 1 error, a false positive, the determination by the proposed definition of reasonably stable that water levels are actually declining, that they're not reasonably stable among a set of wells that we're hypothesizing represent, in fact, reasonably stable. So this analysis is evaluating the type 1 errors of this test, but not the inverse, which is the tendency of a test to characterize water level behavior as reasonably stable when the department might, based on other analyses, determine that it's actually in fact declining. So there's this analysis is structured to look at only one part of the problem, and it shows that the proposed rate test is relatively good at solving that problem of avoiding type 1 errors compared with a standard rate test. It doesn't address the inverse problem of retaining sensitivity to declines the department is instead at the moment developing analysis to understand the impact of additional declines on dry wells as a separate piece that we'll talk about in the next RAC meeting. But I just want to acknowledge that that's how I see these pieces fitting together. Just as we looked at with the total declines, the percent of time that wells remain with a rate of decline according to the rate test shallower than some threshold is larger than the corresponding percent of wells that remain stable over their entire period of record. Both for the, if you look at all the well clusters in the blue line, or if you look at the ones that exceed a given rate threshold at some point during their record, they still remain reasonably stable over the vast majority of the record. And that's not that surprising, because we're looking at these wells that are cycling up and down. Of course, most of their record is not going to be these most extreme values, or extreme is the wrong way to put it. Most of their record is not at the bottom of a trough. So to sum it up, this is again the same summary from RAC 7. We looked at wells that represent the dynamically stable range and evaluated the total decline and the rate of decline among them, and have shown what values of thresholds on total declines and rate of decline one could choose to correspond with capturing some percentage of those wells over their entire period of record, as well as considering some percentage of the period of record that remains stable. And the department is really appreciating interest and feedback from the RAC. We're expecting peer review from the USGS today, and we'll be incorporating all of that into our final draft of this memo that will be presented in RAC 8. So with that, we got some time for questions as folks can.
Yeah, before let's check in with the RAC members, see if there's any outstanding questions with the RAC members, and then we'll go ahead and ask the public if they've got some questions. So are there any RAC members? We got Bill. Go ahead.
Yeah, I have a couple of questions, but I think my my questions are my questions going to be addressed at the next RAC member, and I get at the next RAC meeting, and I'm wanting to understand better how this tool would be used in a particular situation where someone, people come and apply, want a permit to dig a well. There isn't a well there currently, so we don't have well level data. Is the assumption that there will be nearby wells on which that one can use this test, and how nearby do they have to be? Can they be, how far away can they be, and all of that kind of thing? If those are the questions that are going to, I'm guessing those are questions that are going to come up maybe at the next RAC meeting, in which case I'll just not ask for an answer now.
Justin?
Yeah, maybe just a short answer, Bill, and I'm not sure if it'll come up again or not. If it does, that's fine. So a couple of things. As Ben mentioned earlier, and as you just said, if there's wells in the vicinity that the hydrogeologist during their review of the application believes are within the same groundwater reservoir or part thereof and are representative, we'll absolutely use those data to assess whether or not water levels are reasonably stable in the aquifer. We haven't designated a distance because the geometry of the aquifer is going to be different in each case. The hydraulic parameters, the transmissivity and storativity kind of affect how close or far a well might be representative. So we're leaving that up to the discretion of the reviewer at the time. In the case where there are no data proximal, or that's the call that's made, there's two options. first of all, the rules as they're proposed allow us to look around and say, is there any well development here? And if there hasn't been any well development, we'll make the assumption that the aquifer is in equilibrium with the climate in general, and we will find that water levels are reasonably stable in that case. If on the other hand, there has been development, just no water level data. So, in areas that developed early in time, in the 50s or 60s, lots of water rights for groundwater went out without any water level monitoring or reporting conditions. So maybe we know there's development because there's a water right there, or there's been exempt use development, but we don't know what the water level trends are. Then the rules require 5 years of data be collected. And that doesn't have to be from a newly drilled OBS well. That could be, the applicant working with their neighbor who might have a well to monitor their well in the spring. But the way the rules are written now, it would be on the applicant to work to collect that data, and we know from the way the rules are written that needs to be a 5-year data set. So that is in general how it would work. Did I cover all the scenarios that were on your mind?
Almost, and that's
Okay.
enough for now. I'll save it the rest for later. Thanks very
Okay.
much.
Sure thing.
Yes, so I see a question in the chat from Kate. I'll let you go ahead. And then if we don't have any more questions from RAC members, there's a question from Kyle. So I'll let him ask his question, but go ahead, Kate.
Yeah, go ahead and answer the other questions. Mine was just a comment and question about the Hill method and determining stability with wells that have a long period of record, and there's a long period of record of precipitation as well. So it's just a thought I'll follow up on later.
So Justin and Ben, can you maybe review that and we can, okay. Okay, Kyle, go ahead and ask your question.
Yeah, I was just wondering if there's an example of a hydrograph that fails the test. Those two that you presented, intuitively, you look at the hydrograph over the years, and there you can just discern that there's really not a trend, and that's pretty obvious. What does one look like that maybe at the margin or does fail the test? Do you have an example, just so I can see what it looks like and how this technique applies to something that is a multi-year declining water level trend? Do you have one?
So absolutely. I'm not sure if Ben will have it able to pull up on his screen, but I did show that example in our presentation to the commission, I believe, in December. It's an example, but certainly we've got other examples. I'll see if I can yank it up here as well, and we can flop it on the screen. Or I don't know, is that something you've got quick access to?
Yeah.
I apologize. I haven't been tracking this very closely, so.
I was going to suggest we take, John had his hand up. Maybe we could take John's question while you guys look for that to address Kyle's question. John, if you want to go ahead.
Sure. This may be for specifically on Justin, that what you just described as far as I've got an application in there that there's no wells in the area no matter what, that 2 dry holes were drilled, like 7 and 15 miles away or something. And so per your memo, OWRD said it must be in equilibrium and not over appropriated. Water Watch immediately paid the few $100 to protest that. Is there any avenue for that to go through, or is it sit in the contested case pile for quite a while? And thanks.
Well, let me turn. So I'm not going to address that particular application, but I will turn that around and put it in the context of the reasonably stable water level discussion we're having now, which is, again, our current rules as the statute and rule work together say that water is available if it's not over appropriated. And we look at one measure of over appropriation that we can measure directly with water levels, which is, are water levels excessively declined, or are they head in that direction? And with the situation that you mentioned, that sounds similar to what I just described to Bill, where we've got in the proposed Division 8 rules, you know, if we find there's no development in the area, we can assume reasonably stable. So under the proposed rules, that, you know, that's what we would do. So I can't opine on how that might work out with respect to a protest or not. So.
Okay. Thank you.
Yep.
I guess back to Kyle's question now.
Yeah, oh, there we go. Ben's got it pulled up. So, so this is, well, it's a couple of examples of what we've talked about. First of all, it's a composite hydrograph for a location in the Harney Basin, the Weaver Springs area, which is where we have significant declines. And I had this in this presentation mostly as a discussion of how we acted in the past and how, you know, if we had these proposed rules in place back in the day, what we would have done instead. So here's a hydrograph showing water levels from the 70s through the 90s with a little sinusoidal curve that we would consider reasonably stable. And then water levels started to drop in the 1990s. We stopped issuing rights here in 2012 or 13, about the time that the hydrograph reached the point of declined excessively. However, under the proposed new rules, with the proposed definition for reasonably stable water levels, we would have found water levels not reasonably stable a few years earlier, about 2007-ish. So again, this gets at applying the proposed rules to an existing set of hydrographs, a composite hydrograph in this case, and how it found reasonably stable for water levels right up through about 2007. And that water level shown about 2007, where the shading goes from blue to red, that's the water level that tripped the condition that found not reasonably stable water levels.
Got a thumbs up from Kyle, so I think that answered Kyle's question. Do we have any other questions from members of the RAC or from the public? And well, give folks a minute. Ben, if you could just go to the last wrap-up slide with the next steps there. Okay. So we have asked for input regarding the information we presented today, as well as the, you know, the same information that was provided yesterday. We had a different set of folks attend that session. Give us, you know, your feedback on what you heard, or if you still have questions, if you can get those to us, to me. I dropped my email in the chat by COB today, actually, just on this information. And we'll take your input as well as what we get back from USGS and reevaluate as appropriate or needed, so that we can incorporate the feedback into the meeting materials for our next RAC meeting, which is on January 23rd, hybrid, 8:30 to noon. Materials will be posted on the website. Public comment is welcome. And I think that is all we have. So Justin, Ben, I don't know if you have anything to add. If not, I'm going to go ahead and stop the recording and end the meeting. So
Yep, just
Thanks,
thank
everyone.
for everybody's comments that have come in written and that we've had conversations the last 2 mornings. So appreciate it.
Okay, thanks, everyone. Happy New Year.